Hello, everybody. Dr. Mandis is here, talking to you today about empirical molecular formulas. This is a concept that is often done when you're learning about moles for the first time. Sometimes people introduce it earlier and then come around to it. There are different types of writing formulas of compounds. It really depends upon your point of view. As a chemist, in research, you do empirical formula calculations a lot because you get it from elemental analysis data. From that, you derive these empirical formulas. Then from there, with some mass spectral analysis, you get a molecular ion, and you can figure out this molecular formula gig. So this actually has a great basis in real life, even though I just had that argument with a teacher a couple days ago that doesn't. But not everybody knows everything. I certainly don't. But anyway, you got molecular formulas and empirical. Molecular tells you the exact number of atoms in the molecule, the exact ratio. Over here, I got some water, and I'm saying, hey, water is a 2-to-1 ratio, 2 H's to 1 O. Glucose, C6H12O6, could be fructose for all we know, but it's a simple hexose sugar, C6H12O6, gives you a ratio of 6 to 12 to 6 in the molecular formula. But the empirical is the simplest ratio. Empirical means from the data. That's why I went on a little bender about saying, hey, it's from your elemental analysis, your percent comp, not to just intimidate you or sound whatever. To say, look, empirical, lots of people just say it's the simplest ratio, and it is, but empirical evidence is evidence with experimental data. Do you have something to back it up? So empirical formulas get derived from the data already, and that's why they're the simplest ratio. It's 1 to 2 to 1 for the glucose because 6, 12 to 6. You can divide each of those by 2 and you get 1 to 2 to 1. The water happens to be empirical and molecular the same gig because 2 and 1 is the simplest ratio. Alrighty, let's do an example of just calculating empirical formula. You got this wickedly long compound here that I kind of made up. Okay, if you have that, you have a 6 to 12 to 2 to 2 ratio. You can start off by dividing by 2 and see where that gets you. And you get 3 to 6 to 1 to 1. You can't get smaller than 1. So that's our simplest ratio. That would be the empirical formula. If you notice these ratios, 6 to 12 to 2 to 2, 3, 6, 1, 1, those things are counts. Okay, so those are moles. This is a mole ratio we're developing. Okay, so the ratio of atoms are counts. Okay, therefore they're moles of atoms. So subscripts, you don't think about it too much. That when you say H2O is 2 O's and 2 H's and 1 O, that's a mole ratio. Okay, because think about it. In a gallon of water, how many molecules of water are there? There are many moles of water in a gallon. Okay, so the ratio of atoms could very well just be a ratio of moles too. You can do the conversion. Alrighty. So here's a gig. Empirical ratio is a whole number ratio. It's the simplest. To sum it up, molecular is the actual. Sometimes they're the same, but often they're not. Okay. By the way, because, and might come up with this later, but because we're talking about molecules here, okay, you can't have a molecular formula of like an ionic compound. Ionic compounds don't form molecules. To have a molecule, you have to have covalent bonding. So this really is applicable to covalent molecules. Empirical formulas are written. Every ionic formula is an empirical formula. Right, but anyway, so say we have the molecular formula of our hexose, our glucose. Okay, the empirical formula, yay. You can calculate the molar masses of those, and I'm going somewhere with this. If you notice, this is a ratio of 6, so is that. Alrighty? So we divided by 6 to get the 1 ratio. And usually what you do is you're coming this way as the chemist, then you go back up that way, multiplying by 6 to get to the molar mass of it, okay? But as a chemist, often what you have is this is what you're trying to verify. You don't really have that. I did an experiment to get that, you know? So this you could calculate from because you have a chemical formula, and from here you're going to go up. But the only reason we knew to times by 6 here is because we knew the ending point. What if you don't know the ending point? Somehow we need to figure out some groovy little mathematics here to give us the ending point or some experimental data. We need something to help us, let's say, multiply by what? Okay, to get to what? Okay, but let's just do some examples and this will all get worked out. A sample contains, say, 2.17 moles of carbon and so many moles of H. What's the empirical formula? Empirical formula is just a ratio, the simplest ratio. So make a ratio. Okay, carbon to H. A lot of people don't know how to do ratios, to be honest. You can just sort of say, well, looks like this is twice that. The math that you're actually doing is you take each value and you divide it by the smallest. It might sound trivial, but how would you do a ratio of like, 2 trees to 4 kids that want to climb in the trees to, I don't know, you got 12 squirrels that, want to be in those trees. I mean, what if you have more than one thing? You divide each by the smallest, then you get 1, 2 to 6. Okay? So that's what we're doing here. Divide each by the smallest. The units are canceling, so we have dimensionless numbers that are whole numbers, and subscripts don't write units after them. They're just whole numbers. Okay? So there we go. There's our 1 to 2 and our groovy little ratio of 1 to 2. Alrighty? If, say, this wonderful little compound, okay, has a molecular molar mass of 42.09, could you tell me the molecular formula? All right, there's lots of ways you can finagle it, and students that don't study do all sorts of groovy stuff on tests to figure it out. The easiest way to do it is to do the ratio. Molecular molar mass divided by the empirical. 42, how do you get the empirical? You add it up. This is 12.01, this is 2.02, so you just add it up. And you do the math, okay? The way you get that, I can scroll back up to wherever that was, this 180 divided by 30 gets us to our 6. So we're basically doing this division to get this number, okay? And that number is going to be really important because this 3 is then going to tell us that we need 3 times as many in our ratio. And so we take our empirical, multiply it by the 3, and we get a molecular formula C3H6, and so we have our propene. Alrighty. Sometimes you don't have moles. I mean, usually you don't have moles, okay? If it was me as a teacher, the moles are given in multiple choice type problems. Real problems, we got to work it all out. You're going to be given something else to get to the moles, okay? Usually you're going to get the moles from grams. So we need the grams of each atom. But usually I don't give the grams either. You're often given percentages. And as a chemist, you would do an elemental analysis. So some lab can conduct that for you, and you get your percentages that way. And you sort of want to match that, calculate an empirical formula to match that to what you think you have. Because just because you make it, you say you make it, you got to prove that you make what you have. One of them is to calculate is to determine the empirical formula experimentally from the percent composition data. Alrighty. So from the percentages, you can get grams pretty easily if you just assume you got a 100-gram sample. If something's 30% oxygen, well, assume you got 100 grams of it. 30% of 100 grams is 30 grams. The percentages are going to become grams. You can do this assumption without you're allowed to do it because the empirical formula is the empirical formula no matter how much of the sample you got. You can pick any sample size. You can pick 0.2846 gram sample and do the percentage off that. But why? Just assume 100 grams, and then it's really easy. Just percentages become grams. Most students, just percentages become grams. They just move along. Don't even show me that work, okay? So here's the whole gig overall if you want this for your notes later on. First, second, third, fourth. This is what you have. Percentages become grams. Convert grams to moles. Get your groovy little ratios that we showed earlier, and then use those answers for your formula. The thing about it is this little note. If you don't, when you do your mole ratio, if you don't get pretty much a whole number, you don't get like 2.02, but instead you get like 2.33, that's an issue because you should get a whole number. If that happens, then that means you probably have a molecular formula that doesn't have a 1 in it. Don't go there. It does. All right, what you need to do is multiply your ratios to get rid of that fraction. And in my example that's coming up, I'll show you what to do, okay? Just remember, if you have any hangers on, don't just round it off, okay? It's important. So let's look at this P and O. You got about 44% P, 56% O. What's the empirical formula? Okay, well, we got percentages can become grams, 43 grams, 56 grams. We're going to convert those to moles. Okay, and we get our moles. To develop the mole to mole ratio, these are not the subscripts. The mole to mole ratio is the subscript. Okay, so we need a mole to mole ratio. Cool. We divide each by the smallest, and then we get a 1 to 2.5. This is what I mean by you got something that isn't perfect. It's not like 2.02, it's 2.5. You have change there. You got to deal with that. Okay, they're supposed to be whole numbers. You can't just round it. You'll get the wrong answer. And it'll become clear in a second. What you do to get rid of it is this 0.5 is a half. So times by 2 to clear the fraction. If it was that 0.33 that I mentioned, that's a third. So times it by 3. So just take the reciprocal of that decimal, and that'll tell you what to multiply by. Like 0.25 would be a fourth multiplied by 4. Okay, so here we're going to times each one by 2, and we get a 5 to 2 ratio. And so, oops, I didn't write out the chemical formula. The chemical formula would be P2O5. And if that, okay, and so you can see that there's no 1 here. By dividing each one by the smallest, we automatically set one of them to 1. And in our empirical formula, there is no 1. And that's where this multiplication comes in to fix all that. All right. Lastly, what's the molecular formula? If you're given, as a chemist, you probably do like a mass spec analysis is one way you get the molecular ion and you get the molecular molar mass. And I say, hey, that's well and good that we had P2O5, okay? But the molecular molar mass is 284 grams per mole. What is the molecular formula? Well, that's what we did, do that ratio like we did before. Molecular molar mass divided by the empirical, 284 divided by 41.94. This number will always be given to you in a problem, unless you're in an advanced chem class and you have to do another problem to calculate it. But first time out of the box, it's going to be given to you. The 141.94 you get by adding up the empirical formula. All right, so you would add up this P2O5 to get the 141.94. You end up with a 2, so you multiply by 2 to get P4O10. If on a test you end up with a fraction here, you did your ratio upside down. Okay, it should be a whole number. You're going to multiply it to make it bigger because molecular formulas are always either the same or more. Alrighty? Well, that wraps up empirical formula calculations. They get laborious, but there's a process to it. Just focus on the process, focus on the units, and you'll get through it. Don't focus on the whole thing all at once. It's too much to swallow. You're smart. You can do this. I know it. Alrighty, so learn it, like it, love it. Take care. I'll talk to you later.